Welcome to the McKinney Amateur Radio Club's Amateur Extra License Prep Class for tonight. I'm Bob, K5CRX. Tonight we'll be finishing up the session on receivers and filters, which we started last week. There are about 18 questions remaining in that session for us to complete that, and we'll do that. Then we'll go on to oscillators and frequency synthesis, which gets to be rather interesting. There are about 27 questions in that section. If we still have some time after that, we'll introduce the section on resonance and reactive circuitry. That one will be quite technical, and we may bog down just a little bit on that one, take a little extra time as we go through, but we'll do that as we see the need to do so. By the way, this is session number 6 out of the 10. We have 4 more to go. We might consider doing a makeup class sometime, maybe a supplemental on a Saturday or another night, if that works better for everybody, if we feel we have the need for that in order to be ready to test at field day. Of course, as we've said before, as we get into the next couple of 3 sessions, there are fewer questions listed for that, so we have some built-in time there to make up what we may be behind on a little bit right now. I don't think we'll be in trouble, but we always have the option for a supplemental class if we decide that we need to do that. That certainly won't be a problem. So we're looking forward to testing at Field Day 2026. Again, welcome to the session, and we will begin very shortly. Resume recording. Okay, let me go share my screen now. And let's see, we want to get the right one. That one. Share. See, slideshow. Come on, slideshow. Be nice. From current slide. Okay, are we looking okay? Everybody see me okay? Or see the screen okay?
Yeah, I'm good. John Cash.
Good. Okay. All right.
Okay.
So we had stopped at a question at ED4 D10, I believe it was last week. Anyway, slide number 66, as I had written it down. E4 D10, we had done what was the last one. So we pick up at 11 here on this one, and we'll go on from there. Again, we're finishing up the receivers and filters and all that good stuff that we had from the last time. So here goes. Odd order intermodulation products created within receiver are particular interest to what? The odd orders will mix with other things and are likely to be within the same band that we're listening to, as opposed to the even orders, which get out of the band. So the answer then obviously is A. As always, I'll have the description of it in the next slide. If you want to talk about it, stop me and we will. Otherwise, I'm just going to go on. We're just going to do the questions and go right straight on through. Okay. How does a diode envelope detector function? Very good, except that's not one of the answers. The diode is a rectifier, so that probably gives it away right there. Rectifies and filters the RF, takes out the RF and turns the AC into a not pulsating DC. What type of detector is used for demodulating single sideband? And I have to watch this one myself. And I added a slide right after this that I'll show you. Single sideband uses a product detector in order to pull the audio out of that single sideband signal. I don't know why and I hope I'm not messing up by telling you this, but the discriminator is always something that gets in my way. The discriminator is used in FM to recover the audio. Use an FM discriminator to recover audio there. So if that helps you any, discriminator, FM, product detector, single sideband.
And that's upper or lower, right, Bob?
It doesn't matter. It doesn't matter. Either one. Yes, sir. Okay, principal frequencies that appear at the output of a mixer. You'll recall when we mix 2 signals together, we get the 2 original signals plus the sum and the difference between of those 2 same signals. So that leaves us with answer number C. And that's just one of those givens. What occurs when the input signal levels to a mixer are too high? Well, generally, anytime we see some kind of signal being too high, we're going to be generating spurious products, generating junk that we don't want, and that fits the description here as well. We get spurious mixture products if it's too high. What of the following types of noise are removed by a noise blanker? Now remember, a noise blanker is intended to pick up things like ignition noise, those impulse type noise things that pop up and pop down. I just gave it away, didn't I? It's the impulse noises, like ignition noise primarily. That's one of the big things. Or if you have any sort of interference that pops and goes up and down, it can also work with some lightning noise, things like that. Okay. Which of the following types of noise can often be reduced by digital noise reduction? Well, digital filters, as you know, are wonderful things in reducing noise. The broadband white noise, that kind of noise in the background, can be reduced by that. Ignition noise, they can also take care of a lot of that. Power line noise, which is usually the hum and other things, which means that all of those answers are correct. What type of electrical interference can be caused by computer network equipment? You remember there's lots of little oscillators inside the computer, little clocks and various gates and whatever else. And those things can appear as very unstable modulated or unmodulated signals at certain frequencies as the computer brings up or turns off those different oscillators that it uses. Okay. Which of the following can create intermittent, loud roaring or buzzing AC line interference? Arcing contacts in a thermostatically controlled device cause some buzzing and popping, carrying on. Defective doorbell transformer, in other words, if it has a bad connection, it's doing some arcing, can cause a lot of roaring kind of noise. A malfunctioning illuminated advertising display, we're talking about a neon display there primarily, can cause a lot of noise. So again, that is an all of the above. What causes interference received as a series of carriers at regular intervals across a wide frequency range? What causes those kind of things? Of what's listed there, the switch mode power supply is the most reasonable one. A radar transmitter will give you intermittent noising. A wireless security camera can just give you background noise. An electric fence will give you pulsing noise. So the switch mode power supply is the only choice for that answer. Where should a station AC surge protector be installed? At the single point ground panel. Wherever all your ground points come together, that's the place to install your surge protector. What undesirable effect can occur when using a noise blanker? And again, we're talking about the noise blanker, which is going to take care of impulse noise or pops and clicks. If you have really strong signals there and it's turned on, it can actually clip those strong signals, which makes the signals distorted, and it may even cause it some spurious emissions because it's messing up the signal coming in and causing it to mix with other things that it normally would not have done. So it caused distortion and possibly some spurious emissions. What could be the cause of local AM broadcast band signals combining to generate spurious signals on the medium frequency and high frequency bands? You remember we talked about this, that metal connections, for example, the wires that ground the electric poles outside, those metal connections can get some corrosion. That corrosion acts as if it were a diode, and it will actually demodulate the AM signal. And then the wires that are there will actually re-radiate the thing again. So you can get those crazy spurious signals that sound like AM radio signals. So the thing there is the corroded metal connections. What is direct sampling in a software-defined radio, or SDR? Direct sampling means we sample the RF signal coming in directly digitally without mixing it with anything else first. We don't use a local oscillator to mix it first as we would in a regular radio. So the RF is digitized A to D without being mixed with a local oscillator. Direct. Dither, with respect to A to D converters, dithering is when we introduce just a little bit of noise intentionally, which will reduce the overall noise coming out of the particular converter. It's just one of those quirks of filters and electronics and A to D converters that we have to deal with. Add a small amount of signal, it's called dithering. An SDR receiver is overloaded when input signals exceed what level? We're talking software-defined receivers again. Oftentimes they're using direct sampling like we talked about. That is, they don't have a local oscillator up front, so they're taking the RF right in and converting it into something they can work with. So what's going to, excuse me, What is it going to be overloaded? What's it going to take to overload it? It's going to be when the reference voltage of the analog to digital converter has been exceeded. We have a reference voltage that when the chip that handles that tries to get higher than that, obviously it can't go higher than its reference voltage, and it bottoms out, if you please, or tops out might be the right way to say that, and ceases to really work. You don't get reception then. And that finishes up that section. That's good. Let's kill that one. Okay, any questions about that before we jump into the next section? You guys are just too easy on me. That's all I got to say.
Bob?
But it's nice. Yes.
John, say,
Yes.
could you leave the answer up for just about 2 more seconds? Just so I know, sometimes you click them off pretty quick from my point of
Okay.
view.
Sure. Slow down just a tad on the answers.
On the answer,
Absolutely.
just before you click off the answer, if you could, a couple
Good.
more seconds.
Yes, please. Thank you for letting me know that. That's the stuff I need to know. I may be thinking ahead and just click it without even thinking. So, and then if I do that, say, wait, back up, or just say, hey, back up. And I can back up a slide very, very easily. It's not a problem at all. Thank you. Anything else from anybody? All right. Let me share one more time and let's see what else we can get into here. Oscillators and synthesizers. I can't even say synthesizers. And we're going to do all right. Everybody see me okay? Somebody tell me yes or no.
Looks good, Bob.
Looks good.
Okay, then here we go. Oscillators and synthesizers. That one. Okay. There are 3 major types of oscillators that we use in the radio world: the Colpitts, the Hartley, and the Pierce. They have distinctive characteristics, and I've got a little cheat note here in a minute that maybe will help you remember which is which. If you look at the Colpitts, it's regulated by these 2 capacitors right here. 2 capacitors. So C in Colpitts, C for capacitors, a Colpitts oscillator. The Hartley uses a tapped inductor or tapped coil. So T in Hartley, T for tapped coil, ties the Hartley to a tapped coil. The Pierce oscillator is the one uses a crystal with it. The crystal is used to stabilize the frequency. But a crystal is a piece of silicon, piece of quartz, It's very hard. So it's hard to pierce a crystal, and that's how I remember the 3 oscillators. Pierce, it's hard to pierce a crystal with a crystal oscillator. And so there we are. C, Colpitts uses a capacitive divider. Hartley uses the tap coil. Pierce, it's hard to pierce a crystal. That's kind of silly, but for me, it works. Okay. Let's see. Phase lock loop circuits. A phase lock loop. What in the world is that? A phase lock loop is nothing more than a stable, usually crystal controlled oscillator that has some synthesis after it that can generate all kinds of frequencies. But in order to make sure those output frequencies are absolutely dead on accurate, the output is looped back to the input and compared with that crystal source to make sure that it's in phase and dead in time with that original signal. It's locked to, hence the word locked. It's a loop because we're feeding some of the input back, the output, back toward the input, making sure that the output is locked to the input signal that's coming in from the crystal oscillator. So the phase lock loop. There's only one answer with the word phase in it. When you get to that question, look for the word phase when you see the phase lock loop in that particular question. How do we know this is a Colpitts oscillator? Because it's got those 2 capacitors, C4 and C5, they're a capacitive divider. Okay. Hard to pierce a quartz crystal. There's the little crystal right there on the gate of that FET, which is providing stability to the oscillator for a pierce. And then this, we're not going to talk a whole lot about this. The little triangle there in the middle is trying to illustrate the feedback, something from the input going back, from the output, going back to the input. to make an oscillator work. That's how an oscillator works. We take some of its output, feed it back to the input, which gets amplified again, and it continues to oscillate like that. A sine wave oscillator would generate sine waves, of course. A square wave oscillator would generate square waves, and a sawtooth oscillator would generate the sawtooth that you see there as well. That's kind of really more just kind of a FYI stuff. Okay, a lot to influence the precise frequency of a crystal that's used in a crystal oscillator circuit. The impedance of the crystal's age, how it's held in place, whether it's nice and stable or not, the temperature, and then the crystal's natural parallel or holder capacitance, which is going to be the answer to the question. Over which you have no control. The natural parallel capacitance of it, or the holder that holds the physical crystal, you don't have a lot of control over that. So usually in order to compensate for that, we put a trimmer capacitor, which is a very small value capacitor, adjustable capacitor, in series with the crystal so that we can compensate for any of those natural parallel or holder capacitances that's built into the crystal can itself. Just a picture of two crystal cans, one with a red dot, one with a black dot. Not that that's significant necessarily, but that's how you often see them. Sometimes you'll see them as more of a flat can, like the one over on the left side, that one that says 69403 GQ or whatever that is there. That I don't think that's a crystal oscillator, but it could be. But the two cans there, one with a red dot, one with a black dot, are definitely crystal oscillators in a little aluminum container. Of course, that aluminum container helps give them some temperature stability and gives them mechanical stability, and also eliminates any moisture from getting in there and causing any corrosion problems. Okay, again, just demonstrating how an oscillator works. We take a sample from the output, feed it back to the input, which causes it to feed on itself, if you please, to continue the oscillation. That's really what that thing is trying to say. One of the things that we used to use a lot of, I've not seen this lately, but I bet they're still out there. It's called an NPO capacitor. Be a small, usually ceramic type capacitor, a little round thing about the size of a pencil eraser to about the size of a penny, depending on its value. And it would be stamped on there, NPO, so that you knew that it was an NPO capacitor. They're sometimes called negative, positive zeros because they're so temperature stable. Many capacitors will drift with temperature. The NPOs did not. So that was one of the ways to compensate for frequency drift with temperature, was to use NPO capacitors. Piezoelectricity is another one of those things. That crystal that we're talking about, that quartz crystal, is a piezoelectric device. If we put a voltage across it, it will tend to vibrate, or it will tend to distort in the process. If we put a frequency into it to physically move that same crystal, it will tend then to generate a voltage. So it has both ideas. Both of the things behind it. If you stress the crystal, it generates an electrical voltage. If you apply an electrical voltage, it deforms the crystal. So that's the heart of many of the frequency oscillators that we use. They use crystals for their frequency reference. Okay, let's see. Can be described in purely electrical terms. It's an RLC circuit. Series resistor inductor capacitor circuit is the equivalent to it. But it does have a small amount of capacitance in parallel with it, sometimes called the holder capacitor, that doesn't necessarily have anything to do with the holder as such. It's just that's what it's called. And again, we can put an external little capacitor, a variable capacitor, and parallel with it, and compensate for that as we need to. If you apply an electric field to the crystal, it will mechanically deform, and that's one of the features that we use of it. They're the heart of nearly all precision oscillators, as it says there. At 10 gigahertz, 24 gigahertz, which is that's cranking. Oscillator stability is very, very important, because just a small amount of drift will put you way out of frequency from where you want to be. Microwave operators who run beacons many times use the GPS satellite system. There are GPS receivers that can give you time accuracy within millionths of a second. Some use a rubidium standard. I actually have one of those. You can buy a surplus rubidium unit, usually about $50. Set up a power supply with it. You have to allow them to warm up good, but they will give you an absolutely totally stable, accurate 10 megahertz signal out, square wave out. That's accurate. I believe the rubidium is accurate, something like 10 to the minus 56. Some just almost unreasonable amount of accuracy out of those things. And as I said, you can buy those surplus and actually build one. I do have one. They're pretty neat. So GPS is one way to have some get sync, and then the rubidium standard is another way. And then a temperature-controlled high-Q dielectric resonator. All that means is a special circuit that has temperature compensation in it to make it stay at the same temperature all the time will make that work. So the answer to that question is actually going to be all of the above. It's going to be all three of those. Okay, we got a thing called microphonics. If an oscillator doesn't have all of its components mounted securely, any little bit of vibration will transfer into one of those components, especially the crystal. Excuse me, let me let somebody in there. Especially the crystal, and you will actually hear that on your signal going out. You'll hear the banging or sound like paper rattling or something like that. So in order to prevent microphonics, we have to make the components mechanically rigid. They just make sure everything is well attached and padded and insulated and isolated so that outside vibration do not affect the components inside to give us microphonics. Okay, we do that by physically isolating it. That is, we insulate and isolate it so that it doesn't have a chance to vibrate. Okay, frequency synthesizer is where we take usually a crystal oscillator, do some electronic processing through counters and various things to synthesize another frequency, maybe above or maybe below. Back in the old days, he mentions being rock bound before we had all the digital stuff that we have now. Most hams had a collection of quartz crystals at various frequencies. So if you wanted to transmit say on the 40 meter band and you wanted to transmit on 7.125, you had a 7.125 crystal you would plug into your transmitter that would hold you on frequency. That was called rock bound. You were bound with the number of crystals that you had. So making contacts was a little bit more difficult because you didn't have the leisure as we have today of just dialing in the frequency that you want. You had to stick with whatever your crystal told you. Of course, your receiver could go anywhere you wanted it to, but your transmitter was locked to that particular crystal. Nowadays, with frequency synthesizers, we don't have to worry about that. And boy, am I glad we don't. Another little diagram of a phase lock loop circuit. Crystal oscillator over there on the left. Some digital counters or dividers or whatever's necessary there. We may be multiplying the signal up or we may be dividing the signal down depending on what we're trying to get out of that. Runs through the phase lock loop, which has a divide by N, you notice on its output, a voltage controlled oscillator, meaning that oscillator its frequency is controlled by the input voltage off the amp side. So we'll take that output, divide it down, and so we can put it into a phase detector and see if that frequency is too high or too low. From that, we can generate an error voltage, which eventually gets fed back to the voltage-controlled oscillator as a voltage change, which corrects that particular voltage-controlled oscillator to bring it back on frequency. So again, a big feedback loop inside that phase lock loop. That's a whole bunch at one time. Any questions or thoughts on that before I move on? Okay, moving right along. Direct digital synthesis allows a single chip to handle a multi-loop synthesizer circuit in your radio's local oscillator. Boy, that's a wonderful thing that we've got with the DDS, direct digital synthesis. It's not a pure sine wave output, but it works fine. It has a very, very fine frequency resolution, even to fractions of a hertz if necessary. And they also have a very low noise floor, meaning they don't generate a whole lot of noise, which is nice. Within that chip, to make it work, there are components, and this is the answer to the question. It has a phase accumulator, a lookup table, a D to A converter, and a low-pass anti-alias filter to keep the output nice and clean. And that lookup table we'll talk about a little bit more on another question. Within the direct digital synthesizer, the lookup table samples the nearest available voltage levels in the digital D-Day converter that represent the desired output. In other words, we're telling the digital to analog converter that we're going to look in this table. This table is going to tell us we need to have 0.3 of a volt just to pick something. 0.3 of a volt means a certain frequency or a certain output. And if we want to go up, we'll look up another value, or we'll look up two values and sum those, or take the difference between values, play with the math on those things in those lookup tables. But obviously the big point behind it is the direct digital synthesizer allows us to have almost innumerable numbers of frequencies, and it's able to provide those by looking at the lookup table. Unwanted components of a direct digital synthesizer. You can get spurs at discrete frequencies at every so often up the band. A lot of times you'll see on your radios that have DDS, every few kilohertz, you'll get a little birdie or a little beep, and you'll see those things. Sometimes they can be filtered out, sometimes not. But they're very discrete, they're very regular, and they're very, very annoying to boot. All PLL circuits will have a certain amount of phase noise, byproduct of just what they do. They can interfere with the reception of weak signals. If the phase noise is too strong, it can swamp a weak signal. That's really what we're saying there. Nyquist sampling theorem, you don't have to necessarily remember that specifically, but tells us that to sample an analog signal, you need twice the highest frequency signal for the sampling mechanism. In other words, if we want to sample a 1 megahertz system, we need to be sampling at a 2 megahertz rate, twice the rate of the frequency of interest. Okay. Dynamic range of a digital converter is a little bit different than we talked about dynamic range earlier on a standard receiver. Dynamic range on a digital converter is equal to the power ratio between the maximum and the minimum signals that it can handle, which is pretty much the same as the definition we use for dynamic range of a receiver in general. And the question they're going to be asking about this is, how many bits does it take in order to cover everything we want to cover? The answer is 10 bits. Now, you can see where they've gone through a lot of math there using all the different logarithms and stuff. So if you're a mathematician and you want to do that, by all means, but it's easier just to remember 10 bits. 10 bits is 2 to the 10th power, and the powers of 2, which is 1,024, which gives you need 1,000 possibilities. You have 24 extras by using 2 to the 10th power. 10 bits is the answer that you're looking for. The main engine of digital signal processing is the fast Fourier transform. What does it do? Converts complicated frequency domain signals to time domain signals. So fast Fourier transform, fast transform, frequency domain converts to time domain. Transforms to time domain. I don't know if that helps you remember that or not, but frequency domain to time domain. Frequency domain, you remember, is where we go on the horizontal axis in frequency, where time domain, we go on the horizontal axis in time, in microseconds or milliseconds or whatever we need. Makes it much simpler to deal with in the time domain when we're dealing with those things. Frequency domain to time domain. Digital sampling is labor intensive. That is to say, that chip is very, very busy doing what it does. Sometimes it's effective to remove some redundant or unnecessary samples to speed things up. So, I mean, if you got something that you don't really need, why process it? That's the idea behind it. So to speed it up, sometimes we can remove what's unnecessary. Okay, let's see. Process of digitizing is essentially identical to mixing in the analog circuit. Mixing, you remember, is where we take two signals, mix them together. We get the two original frequencies and the sum and difference frequencies out. However, here, the image frequency is one of the things we have to watch out for with A to D converters. It's called the alias frequency, but it's the same as an image frequency. Usually there'll be a frequency above one of the desired frequencies that we're looking for. They're usually not desirable. They have to be filtered out so that they don't get in the way of the real signal that we're trying to hear, trying to listen to. In any digital processing scenario, what's a digital oscilloscope or an SDR radio, that particular theorem is there. The bandwidth of the system is dictated by the sampling rate, which has to be, again, twice the frequency of the highest frequency that you want to observe, want to look at. Meaning bandwidth is covered by your oscillators being twice the frequency of what you're wanting to look at. The dynamic range is determined by the number of bits in the sample, or it's called sample depth, same thing. That was that 1024 bits that we talked about just a moment ago. An FIR filter, and I don't know that I've ever run across this one before, but an FIR filter does not reuse taps. Taps are like the ports, as they're called, in the old analog filters. It's a place where we put a signal into a point, and we delay things just a little bit at that point while the system processes that data, then passes it on to the next point, or the next tap, as it's called in digital, where it goes through again. There's a little delay there to allow time to process. Then it passes to the next tap. Now, when we talk about time to process, we're talking in nanoseconds here. We're not talking about great periods of time, obviously. So the FIR filter does not reuse taps, has the same amount of delay for all frequencies of entry. It's much simpler and much more likely to be stable, as opposed to the infinite impulse response filter, which is one you don't see very often. In the digital filter, taps are equivalent to poles in an analog filter, provide incremental signal delays for filter algorithms. Those little delays, again, as I said, are used to give it time to process the signal and then spit it back out and then go to the next tap where it gets processed again till it comes out with what we're looking for. A digital filter can simulate a very complex or expensive analog filter by using more taps. More times we put it through the filtering process, the better it's going to be when it comes out the other end. More taps, the better. Okay, and that's the discussion part. So I'm going to get out of this one and stop sharing. And we're going to go to share the one that gives us the questions first and then the discussion so we can go right on through. Any questions about anything so far while I'm setting this up?
Not yet.
Okay, we'll just keep on trucking. Again, please slow me down. Not a problem. Okay, resonance is going to get a little tacky, but hopefully not too tacky. And we'll try to explain some of the things that go on as we go through this and where it makes sense to do that. Eli the Iceman, brand that into your brain with a branding iron because we're going to use that a bunch, both in this session and in the next session that we have as well. Okay, circuits and resonance. Coils have inductance, capacitors have capacitance. That makes sense, doesn't it? When they're at resonance, when the capacitive reactance equals inductive reactance, that is to say, when the amount of resistance to current flow through the device, through the coil is equal to the resistance to the flow through the capacitor, well, those two are equal. That's called resonance. At resonance, voltages are higher than the applied voltage can be present inside that particular circuit. That's because in a resonance circuit, the current is going back and forth between the coil and the capacitor. It's not consuming the power, it is merely storing it. So we store the power in the inductor in the form of magnetism. Once it's stored, then the magnetic field starts to collapse and it regenerates that same voltage and current that was there, which is passed to the capacitor. The capacitor then stores the voltage buildup again until the magnetic device, the inductor, runs dry. Then the capacitor feeds its load back into the inductor and charges the magnet back up again, or the coil back up again. So we go back and forth. The thing is, out of this one to remember, at resonance, voltages are higher than the applied voltage in many cases. At resonance, capacitive inductance, and capacitive reactance rather, and inductive reactance are equal. I have to watch getting my tongue tangled here. Okay. Again, this is one of those. It's probably best just to memorize the answer 3.56 megahertz when you get to the question. You can figure it out if you want to, using these different formulas to figure things out. but it's probably easier just to remember it, not to become a mathematician. Those are the frequencies, and I can send you a copy of this if you'd like to have it, or maybe you have it already someplace. The formula for inductive reactance is 2 pi times the frequency times the inductance. Frequency in hertz and inductance in henries. Normally, anytime you see these formulas, unless it's otherwise specified or been compensated for, we always use the native values, such as in inductance, it's always the native value Henry, and in capacitors, it's the native value Farad, even though those terms are usually way, way bigger than anything we'll ever be dealing with. We're dealing in millihenries or microhenries. We're dealing in microfarads or picofarads. So, sometimes you'll see us play with the exponents because in order to compensate for that. But these are the basic formulas. And then to come up with the resonant frequency using those formulas, 1 divided by 2 pi times the square root of LC, square root of the inductance, times the capacitance. And again, those are in inductance and farads, capacitance, inductance in henries, capacitance in farads, but normally those will be given in micros or smaller. And so you'll see some compensation using powers of 10 in order to call like 10 cubed or 10 to the minus 6, etc. So you'll see those quite often. And then they want us to show that we can do this. The answer is 7.122 megahertz, and it's probably best just to memorize the answer. However, if you want to go through that, this even shows you the strokes to use on your calculator. 50 times 10, take the square root of that, times 6.28 gives 140.4. 140.4, we're going to hold on to that number, clear our calculator, put in 1 million, because we're dealing in megahertz. Divide by 140.4, which is 7.122 kilohertz, but we want megahertz. So we got to move the decimal point 3 places to the left to get megahertz. Again, it's probably easier just to remember 7.122 megahertz. Okay. Why do we have those big loading coils on some of our mobile antennas? It's basically to lower the resistance. That's it in a nutshell. The bigger wire, the bigger coil has less resistance. At resonance, the magnitude of the impedance is equal to the circuit's resistance, because at resonance, capacitive reactance and inductive reactance, for all intents and purposes of calculation, don't exist. They cancel each other out. So the only thing left is the actual resistance. So at resonance, the magnitude or the size of the impedance is the circuit's resistance. Again, stop me if we need to discuss any of those things. I know we're kind of drinking from a fire hose here. Okay, whether the system is parallel or a series resistor, inductor, capacitor, when it's resonant, the impedance will always be equal to the circuit resistance when the circuit is at resonance. We're restating what we just said. One of the several definitions of Q is the sharpness of tuning, or the quality of the tuning. The purpose of a tuning circuit is to be selective. The better it is at being selective, then the higher the quality or the Q of the circuit, which makes sense, doesn't it? Bandwidth is the reciprocal of selectivity, so that the greater the Q, the lower the bandwidth, meaning that if the Q increases, the width of the band that we're going to be listening to will be much narrower. That is, we will only hear what we want to hear. We will select that one signal out of the many and only hear the one that we are wanting to hear. The greater the Q, lower the bandwidth, the greater the selectivity. A parallel circuit at resonance is similar to a tuned trap in a multi-band trap antenna. At resonance, trap keeps the power from going any further. Be assured there is maximum circulating current within that parallel circuit. However, that is the current that's going back and forth between the inductor and the capacitor, going back and forth, will be going like crazy. It will be at maximum, but it will stay there. It will not pass it through. So we go into that circuit with minimum current and come out with minimum current going to the next stage. That's why we call those parallel resonant circuits traps in an antenna. You'll see antennas advertised as trap antennas. That's what they're talking about. They're putting a resonant circuit at a certain point in the wire that will trap a certain signal and will not be allowed to pass through that trap. We're not even going to talk about that chart. I don't see any questions on it, and I don't think it's necessary to spend a lot of time on that one. Total current into and out of a parallel RLC circuit at resonance is minimum. We just got through saying that. Okay, in the old days, we would dip the plate. It was called, you would peak the grid and dip the plate when you were adjusting the tuning of the old tube type machines. At any rate, current into and out of a parallel circuit is minimum at resonance. Okay, resonance, inductive reactance equals capacitive reactance. Voltage and current are in phase. Now, this is where we start to get in trouble. In an AC circuit where we're going back and forth all the time, capacitors and inductors behave differently. They will cause the voltage and the current for that signal to get out of phase by 90 degrees. And so the magic to remember that is Eli the Iceman. ELI, as you see on the lower left. E stands for voltage or electromotive force is where the E came from, but it means voltage. Voltage and L means inductor. In an inductive circuit, leads current, I, intensity or current. So voltage leads current in an inductive circuit. Okay. Consequently, then, from an ICE circuit, ICE for the C being capacitive reactance, in a capacitive circuit, current I leads voltage E, and that's shown by the two waveforms that they have there with current and voltage being plotted. And both normally will be 90 degrees in its native format that we would normally expect it. The problem with all of that and dealing with it and calculating it is that those waves are going to go through zero. There are times when its value is zero, which causes us a problem with Ohm's law because you can't divide by zero. And that's where this thing called the J operator comes into play. And we're going to see more of that as we go along the way. And again, this is one, it's probably best just to remember the answer minus 14 degrees instead of remembering arc tangent of 10 to the minus 1 of the net reactance, yada, yada, and doing all the computations. Again, if you want to do the computations, by all means do so. Also, it brings, notice the minus 14. The minus sign tells us the voltage lags the current. Now, we got to watch out for leads and lags because they will tend to use both terms back and forth. And I've got another slide here in just a minute that we'll talk about that a little bit further. But anyway, at any rate, if it's minus, that means the overall overriding resonance is capacitive. If it's positive, that means the overall overriding reactance is inductive. Inductive positive, capacitance negative. Okay. And there's all the formula stuff again. Minus 14 to remember, if you can remember that. Another one there. Eli the Iceman comes into play again. Give us another circuit. Again, if you want to divide that out, you can do. They're looking for 63 degrees. The capacitive circuit reactance, the voltage lags the current. You notice they're saying voltage lags instead of current leads voltage, which is what Eli the Iceman says. So you got to watch out and make sure if you're reading leads or lags in order to understand which way it's going, if it's positive or minus. In a capacitive reactance circuit, the voltage lags the current. That is, the current leads the voltage. As that's ICE, ICE, inductance leads, excuse me, pardon me, current leads voltage, which means voltage lags current. Watch out for the two. Voltage lags current is the same as current leads voltage. Current lags voltage is the same as voltage leads current. Eli the Iceman, again, be sure and watch out for that. In Eli the Iceman, we're always talking about leading and not lagging. So just be aware of that when they say leads or lags. It's very easy to overlook the word lag when it comes up. Okay, let's just move on from there. We don't need to talk about that either right now, or that either right now. A capacitor in an ICE circuit where AC current leads the voltage. Word ICE, letter I for current, leading the letter E for voltage in a capacitive circuit. Plain and simple, capacitive circuit. Inductor ELI, says the letter E is ahead of the letter I. Voltage leads current. And it's by 90 degrees normally. Okay, when we're graphing things, this resonance and all these things, normally the x-axis is either going to be the frequency or it's going to be a resistance, whichever it happens to be for us. The y-axis will normally always represent the amplitude, or how big is this value. Oftentimes, and what they're looking for here is that the y-axis will use a logarithmic scale or a decibel scale, which is a logarithmic scale, in order to make it fit on that graph. If it didn't use the logarithmic scale, the graph would be inordinately tall or inordinately long toward the bottom in order to plot that particular value. By using logarithms, we can squeeze it or compress it so it'll fit on the graph. The answer they're looking for there is it's logarithmic on the y-axis. The horizontal or x-axis represents the resistive components when we're talking about impedance. The vertical axis represents the reactive component. If it's an inductive reactance, it will go in the positive or up direction. If it's capacitive, it will go in the negative or down direction. We'll see that come to play as we go through. Imaginary components. Why in the world would we want to have an imaginary electronic component? And this is something that has bugged me. It's just a matter of terms. We talk about an imaginary value. For example, the square root of -1, which is the definition of the letter J. As we all know, you cannot take the square root of -1, hence it's imaginary. But it's used as a trick, if you please, in order to do the calculations and make the calculations of things we do a little bit simpler. So that's imaginary is going to come up here several times more. By convention, the resistance R is plotted on the horizontal, this is the side-to-side axis. The reactance value, the X value, is on the vertical axis. Inductance values go up, capacitance values go down. Inductance values are plus, capacitor values are minus. Reactance value is prefixed with the letter J to indicate that it is the imaginary component of the impedance. Mathematicians use the letter I. We don't use I because I means current, so we use the letter J instead. And when we say imaginary voltage or imaginary current, whatever, we're not saying it doesn't exist. We're just saying that we can't treat it like we do a DC voltage or current, which is always going to be dealing with a constant value of resistance. So it's a way of getting around without having to get into some deep math and calculus. That's really what it boils down to. Am I okay on that so far? We'll see some more of it later. And this is a fairly long slide set too, by the way, so hang with me. We've got about 10 minutes to go. We'll go as far as we can. Okay, and let's see now. There are some questions that use the rectangular or Cartesian coordinates, and there's some questions about polar coordinates. There's a couple of tricks on a couple of these that you can use if you want to, and we'll see those happen when they come up. So let me not spend any time on this one. We'll got to do the actual problems, and we'll see how that plays out. Okay, in the polar coordinates, a phasor is simply an arrow or a vector that shows the magnitude or the size and the phase of an electrical current in a circuit. In other words, we put an XY axis grid up there and then start at the 0 point of that with a phasor, which is just a line, and it goes out to a certain point. How far up it's gone or how far it's gone from the 0 line will be the phase angle. And then the length of the line will be the magnitude. Then we can use some trigonometry to figure out a lot of the other things that we need to know about. Length of the phasor's magnitude, direction of it is the phase angle between voltage and current. Phasor is simply an arrow or vector, shows magnitude and phase of an electrical current, which is what we're after. We use the term complex when we start dealing with this square root of -1 and all those sort of things. To me, actually, it is kind of complex. It's not something that I just lay down and spit it out. I have to think about it hard to get it to come together. Impedance is always a complex value because it has both resistance and reactance, although it could be 0, of course. Even there can also be a negative zero resistance. That's not common, but it can happen. Using the Cartesian coordinates, that is the rectangular coordinates, resistance values are plotted on the horizontal axis, the left-to-right axis. Reactive are pointed on the vertical, the y-axis up and down. Any impedance that has a positive resistance will show to the right. Any negative resistance, if you have such a thing, would show to the left. And then, of course, the up and down would be plus and minus. Inductive reactance to the top plus. Capacitive reactions when we go down or be negative. A pure resistance, that is an impedance where the reactive component is zero, in other words, it's at resonance, will show up on the horizontal axis. That is all you'll see. You'll see no increase or no rise on the y-axis. You'll only see the magnitude indicated on the x-axis, the horizontal axis. Okay, the J operator designates the reactive component that we've been talking about. Know that positive reactance is inductive, negative reactance, capacitive. So we see the term, for example, 50 minus J25 means we have 50 ohms of actual resistance and 25 ohms of capacitive reactance. And we know it's capacitive because it's minus J. If it were plus J, then it would be 25 ohms of inductive reactance. Just remember minus capacitive plus inductive. And there's a figure coming up here that we're going to look at, and unfortunately it's not all on the same slide. And so we're looking at this thing, and we're trying to figure out some values to the different points. Now, again, I'm not going to spend a lot of time on this one because it's too hard to go back and forth between these two slides. When we get to the actual question, we'll see this on one slide. We have the question and this chart on one slide. It makes it easier to discuss. And this is telling us the answer to it. Point 3 is the answer to that particular one, where there's let's see, 3.5 megahertz, and there's 18 microhenries, I believe was the value. And talking about it one more time, we're doing the same thing on this one, but now we're doing capacitive reactance. And again, we'll see that on the real question where we can actually see them all there at the same time. To display the impedance of a circuit with its phase angle, we can use the polar coordinate system. That's the one where we have the phasor that runs out from the center of the x and y axes, and the length of it represents the magnitude. The angle from the zero reference line on the x-axis represents the phase angle between current and voltage. Polar coordinates provide a visual representation of the value of impedance and its phase angle. Okay, a lot of things can be expressed various ways, and of course that's true here. We can use the polar notation, or the polar notation system, polar coordinate system, or we can use the standard Cartesian coordinates if we want to use. We use whatever we want to. In the polar notation, impedance is expressed by magnitude and phase angle. Magnitude is represented by the line. The phase angle is the angle that the line has in relation to the zero axis, x-axis. We're repeating ourselves a lot. I hope you get the idea that this is important to remember. Inductive reactance is up, capacitive reactance is down. Inductive reactance is positive, capacitive reactance is negative. Phase angle is measured counterclockwise, beginning from the positive resistance axis, that is the y-axis line. In a pure inductive reactance, pure inductive, meaning there's no resistive component here, then the reactance would be straight up on the x-axis because there's no resistance. There's nothing to go out on the x-axis to the right. There's no resistance there. So all you would have is a straight up line of positive 90 degrees of pure resistance represented by the reactance of that particular circuit. Okay, let's see. Sometimes we use reciprocal values, and this gets a little confusing for me. I have a chart someplace, and I'm not sure where I put it, that shows the relationship between conductance and susceptance and admittance and all those things. I don't know a way to get around this again, than just to memorize what it's saying. Reciprocal values of resistance, reactance, or impedance. Reciprocal of resistance is conductance, reactance is susceptance, and impedance is admittance. Wow. As I said, I just don't know an easy way to remember which is which. I've not come up with one anyway, so forth. The unit of measure is currently Siemens. It used to be called the mole, which was ohm spells backward, but that's the old terminology. Now we use the term Siemens instead. Okay. To convert impedance to admittance, simply take the reciprocal of the magnitude and flip the sign of the phase angle. That's easy enough, isn't it? A circuit or component has susceptance because it is susceptible to current flow. Okay, susceptance is measured in Siemens. The symbol for Siemens is the letter B, by the way. Now, why it's not S, I have no clue, but the symbol is B for susceptance. It's an imaginary component of admittance. Again, we're talking about imaginary values. Values imaginary not because they don't exist, but because they don't consume power, actually, is what it really relates back to. It's easy to confuse units with symbols. The symbol for susceptance is the letter B. The unit of susceptance is the mho or Siemens again. And we're getting very close, so we'll take this one and we'll stop for tonight. We have several reciprocal functions, 1 over whatever the original value was, which is the definition of a reciprocal, which are very useful when working parallel circuits. 3 most common are conductance, the reciprocal of resistance, susceptance, reciprocal of reactance, and admittance, reciprocal of impedance. All these values have units in mhos or in Siemens, represented by the letter B, you remember. We all remember the mho because you could have mho current flow with a mho, but anyway, that's neither here nor there. Okay, so next time we will pick up right there on slide 44 in question E5A09. Technically, we got a couple of minutes there. Anybody have any questions, any thoughts, any comments, heartburn, headaches, or otherwise?
Can't think of anything right now.
Okay. And by the way, I think I've said it before, but in case I haven't, if you do have a question or a comment, please feel free to email it to me or to text it to me at my phone number. Again, my phone is listed in the invite email, but it's 972-824-3484. And easy email for me is k5crxham, H-A-M, @gmail.com. I'll get the email from there, or I can get the text message that way, either one. I'd love to have any questions or comments that you might have. I may have another little supplemental sheet to send out to you before next week. I'll see if I can get that pulled together. Meantime, though, I think we've done what we set out to do. Any additional comments or questions about anything?
No, sir. Thank you.
Thank you.
You guys are just too easy on me, but I sure do appreciate it. Okay. Good night, all. Have a great evening, and we'll see you next week. Take care. Good night.